So I'm super happy to be back in Jerusalem. Many thanks for the opportunity to come back here and to experience the warmth of the weather and the warmth of the people. And and for the opportunity to have our midrasha here, which I think, I don't know, many thanks for hosting this event. So the event itself is about some maybe slightly involved mathematics, but the colloquium talk, I decided to, 95% of it will be really about very basic mathematics. I don't even know. It's something that probably belongs in the spirit. It's like Whittaker and Watson. It's what used to be called analysis, but now it's no longer analysis. It's not existent. It's about transcendental functions, but it's not really an algebra. It's some 19th century math, which you can still find something interesting in it. And so, I'm embarrassed to, I don't know, maybe just to warm up, is the basic problem is really about just linear differential equation. So F is a matrix, A is a matrix. And for us, A will be a matrix with rational coefficients. So this is a differential equation, has finitely many singular points. And if you start at any point and you go along a path which avoids the singularity, that of course you can solve this differential equation by the theorem we teach our undergraduates. And so the concept of monodromy goes back to Riemann, and it says that if I start at some point and I continue my solution along a certain path, come back, then if I had some initial condition for my matrix at the beginning, and I come back, I get a different value of the solution at the same point, I take the ratio. This will be the monodromy along this path. And obviously, if I compose the path, these matrices will compose, and so I get a representation of the fundamental group minus the singular of my complex plane minus, or complex Riemann sphere minus the singularity. I get a representation by matrices where n is the size of my differential equation. So back in Riemann's time, this was a revolutionary idea. Now, of course, it's not exactly a new idea. And for just to be somehow completely explicit, what would it be for the simplest possible equation if I take just essentially a constant coefficient equation? So I take the simplest, well, not a constant coefficient equation. I take this equation, has singular points at 0 to infinity. And then, of course, I can solve it by just by the matrix exponential. And so if I go around the loop, the log picks up 2 pi I, and my monodromy is 2 pi I. So if A naught is the coefficient matrix here, and my monodromy is exponential of 2 pi I that matrix. And so what we really see is an exponential map from the Lie algebra to the Lie group. And in general, you can think of monodromy. The monodromy data, the original equation is some linear data, something like a Lie algebra. And the monodromy is a group data, something like a group. So monodromy is analogous to the exponential map from the Lie algebra to the Lie group. And so more generally, one can study similar problem in higher number of dimensions. If you have a compatible system of differential equations, this is to say a flat connection on some holomorphic bundle over some base manifold, then similarly you can continue solution along any path. And what you get is a representation of, you take your base manifold, take away the singularity, and if you fix some base point, then the monodromy will act by automorphisms of the fiber of that bundle over your base point. And monodromy is a very important concept, so this is, I couldn't resist quoting from Nick Katz used to have a wonderful web page called monodromy.com. You can read this, I think it's a marvel of wisdom and But so further down that web page, you can find amazing applications in monodromy, maybe in some senses not I discussed here, but maybe some melodic sense and so forth, to solving actual hard number theoretic problems. And so our goal today, so like I said, you can in general study this monodromy map like you would study an exponential map of Lie group with some data like that. But our goal today is not to say something about monodromy of a general equation, but in fact compute the monodromy of some very specific equations. So this is also in the spirit of Nick's, so to speak, work, in that his number theoretic applications happen for very specific equations, not for, you're not. So in a sense, this is maybe described as, so I have a transcendental map between algebraic varieties, and for some specific values, it takes, for some specific arguments, it takes interesting values. Like, maybe the analogies are here, so if I take maybe a J invariant of a complex multiplication curve, that will be an interesting number. So this is, so the equations we want to consider, they're not so, if you open Whittaker-Watson, then there'll be various chapters on various classes of special functions that bear names of different people who actually studied the equations for what they describe. Right? I mean, the actual physical phenomenon people wanted to understand was described by linear differential equations. And those times are long gone, of course. So now the differential equation is just now differential. It is still a linear differential equation. That didn't change. But what is important is that the coefficients in this equation and the coefficients of the solution, they contain certain information about some much more complicated phenomena than just the somehow, we're not. Airy was solving, Airy was studying every equation for the actual shape of the solution. Now for us, the coefficients, the special functions you get as both the coefficients of the equation has a certain meaning, and the solution, what you get in the solution, has a certain meaning in the context of enumerative geometry and representation theory. And I'm going to talk a little bit about enumerative origin, not going to talk about representation theory at all. What I want to say is that these equations, the way they set up, they in fact very naturally come with, so these were differential equations, but in fact they very naturally come with a deformation to Q-difference equation. Still linear Q-difference equations. So maybe before going, so this is a poster, marvelous poster of our midrasha. I hope you I don't know, anyway. So a regular Q-difference equation is an equation of the exact same type as we discussed, except now instead of derivative, I shift the argument by Q, and let's assume Q is less than 1. And this is called regular at 0 if its value of this matrix at 0 is, well, it's non-singular and invertible. It's an element of GLN, and it has the same at the origin. Will have exact same theory of solution as a regular differential equation. And for example, if the analog of the exponential we had this example with the exponential of a matrix. Well, the analog of that would be, so if my matrix, if in this setting my matrix is constant, then the solution is just this. So this is this analog what we had. And one difference with differential equation, so this is a familiar, we teach our undergraduates about gamma functions. So once you get something which is holomorphic in a certain region, satisfy a difference equation, that gives you meromorphic continuation to the whole complex plane. So there'll be no phenomenon of something being multivalued. Instead there'll be some meromorphic solution in a complex plane. And somehow again for a silly example of that, for a 1-by-1 abelian example, if you take this reciprocal of Q gamma function, which you can explicitly give by this product, then by its very definition, this object satisfies, if I shift q by z, means I lose one of these factors in this product, so I get the simplest possible equation of this kind. And you see that this object is visibly going to be holomorphic everywhere for any z other than infinity. And if I write a general solution, if I write a general rationally one-by-one equation, the coefficient of that equation will be some rational function. And so corresponding to the poles and zeros of that rational function, I can write a solution in this form. And you see this is explicitly meromorphic in the whole complex plane. I hope I didn't say anything that somehow required any concentration. And then you define the monodromy. This is a notion that goes back to Birkhoff. The monodromy from, maybe I'll define monodromy going from 0 to infinity. You define it's just the ratio of fundamental solution at 0 and the fundamental solution at infinity. So we will connect back to the monodromy of the differential equation in a second. But so this you have a regular Q difference equation. It will have a solution of a certain kind at 0, and solution of the exact same kind at infinity. There will be solutions of the same equation, so you can take the ratio. That's called monodromy. And to compare and contrast it with the case of monodromy of differential equation, is that this object, there we had many matrices, and the matrices were constant. This object is just one matrix, and it's constant in the sense of difference equation. Means it depends, it's a constant in the field in the differential field. So it means it doesn't, it's really, in the usual sense, it's an elliptic function. It doesn't change if I shift z by qz. So it's really, instead of a whole bunch of constant matrices, I get one elliptic function. And if I go back to this example, if this is my solution at 0, and I write the exact same expression at infinity, I take the ratio, I can explicitly see I'm going to get a rational expression in theta function, which would be like Jacobi's way of writing elliptic functions. Yeah, everybody agree with that? And how does this relate to the singularities to the monodromy of differential equation? Well, if I let my variable q go to 1, in which case the shift, so if q goes to 1, the shift by q becomes kind of like differentiation. And so I get the limit to the differential equation. What does this monodromy really compute? So if I had my solutions, anytime a solution has a pole, since this is, or pole or 0, then since I satisfy the Q difference equation, I'm going to get a whole geometric progression of these poles and zeros. So anytime I have the singularities of my solutions, they come in this kind of geometric progressions that accumulate either. So for the solution at 0, here I gave my Q a little bit of imaginary part to make this a little spiral in, make it for a more distinct picture. But you can make Q real, that will have a straight rays. And so the solution at 0, this will have this accumulation of poles along this spirals. And so in the limit q to 1, you'll see branch cuts appear there. The solution at infinity will similarly have branch cuts at the spirals that go to 0. And it's clear that if you know if you know how one such solution transforms, if solution near 0 transforms to solution infinity, it's clear that you know the monodromy around all of the singularities. Is that clear? So you're done. So this is how this one matrix captures the full data of the monodromy. Make sense? And so now we're coming back to this. Maybe I'll scroll back. So I was saying that we're interested in some specific differential and difference equations that are of either representation theoretic or enumerative enumerative kind of origin. And I'll skip the representation theoretic discussion. I'll go to enumerative geometry. And in enumerative geometry, these things are called quantum differential equations or quantum difference equation. But the quantum, I mean, of course, it's a nice name, but it's really a linear ODE with regular singularities. So there's not so much per se. There's not so much quantum about it. It includes interesting information in the way that I'm going to explain, but by itself, it's a very classical object of mathematics. And so how does this go? So now I'm going to explain what is a quantum differential equation. So this geometrical has to do with counting rational curve in some algebraic variety, or maybe counting pseudo-holomorphic spheres in some symplectic manifold. Let me stick to algebraic setting. So if I have an algebraic variety, then it's the cup product in its cohomology has a remarkable deformation called the quantum product, and the structure constant. So I have three cohomology classes: alpha, beta, and gamma. And I'm going to describe you the structure constant of a new product, which is called this denoted by this star here. So the structure constant means I take these are the structure constants of my product. They are given by counts of all rational curves that meet the three corresponding cycles, where you record the data of the degree of this. You sum over curves over all possible degree, and you record the degree of the curve by a new variable. You give yourself a new variable that is really belongs to the group. You consider it as a variable in the group algebra in the group algebra for h lower 2. So this is where the degree lies. Degree is an element in this group, and so then to record the degree of the curve, you give yourself the corresponding element in the group algebra. But it's or else you can think of z as being a variable in some torus, which is you take h upper 2 and you tensor with c star. In other words, you have as many variables as you have different curve classes. And so this is one. There are many remarkable things about this definition. For example, one, which is not a new fact, but it's still, I think if you haven't seen it before, still remarkable, that this product is associative. It's not, it's clearly commutative or supercommutative, but the fact that it's associative is a surprise. And so in reality, of course, this is, the actual definition of this is not what I explained. It's when prospective grad students come and ask what is it that I do, I draw pictures like this. But then when they come for actual graduate work, then there's quite a bit more that they have to master. But this pictorial definition, and it's a well-defined object. And a very important enumerative information is encoded in this, what's called the quantum differential equation. Like I said, I mean, it is a linear ODE. And it's an equation for unknown function f of the variables. So the variables are the variables z that appear in this quantum differential equation. And you would differentiate, if you differentiate this, and it takes value, the function takes value in cohomology of my algebraic variety. And so if I differentiate it with respect to a variable with respect to lambda, which lambda is so z was a variable in a torus, and lambda is a variable in the corresponding vector space, which is the tangent bundle of a torus is trivial, so you can think of a tangent vector to vectors to a torus, have a constant vector field along a torus. And so lambda sits in that space, which is abstractly h upper 2 of x. And the equation reads that if I differentiate the direction of lambda, this is lambda star product f. So for f, it's a linear differential equation. And it's not an equation with constant coefficient because this product depends on z. Right? It's a linear equation with variable coefficients, and to differentiate some monomial in z with respect to lambda, well, I have z to a power curve, and I differentiate with respect to a class in h upper 2. Well, I have a pairing between h lower 2 and h upper 2, which is the result of this differentiation. So both this equation, both the product starts out as a formal power series, and also therefore also the solutions will start out as formal power series. But in fact, for a large class of varieties so what does it mean? What does it mean Lie theory without groups? So there is a large class of algebraic varieties, which in some sense just as good as a Lie algebra. And which I'm not going to explain what this means. And so then for this varieties X, this is known let's say known for those varieties that we know, it is known. We don't know all of them. So for those that we know, it's known that this is in fact equation with regular singularity, just like I was describing. So this is really, even though it's defined as a formal power series, in fact it converges to a rational function and defines you a linear ODE with regular singularity. So this is some no. But I should point out that in the generality you can ask about in the generality that this quantum cohomology and quantum differential equation is defined, then it is in general it's extremely hard chestnut to analytically continue this series, and so this is something very particular to a very special class of varieties that we consider. The fact that this actual equation with this equation on first of all, it is some global equation, and then the fact that it has regular singularities on top of that, which is super particular. So, okay, all set. I guess I said it here. So we can again reiterate. So for general algebraic variety or for general symplectic manifold, that's kind of an Lyubimchev invariant is very hard to get your hands on, and to prove any kind of analytic properties about them extremely hard. But for a very specific class of X, we have both the remarkable fact that this quantum connection is in fact a connection with regular singularities, and generalizes many important equations of representation theory in mathematical physics. By mathematical physics, I mean the kind of like a Knizhnik-Zmolodchikov equation in conformal field theory, this type of equations, and the monodromy of this equation that has all sorts of different interpretation incarnations, including for example, and so all these varieties X, there is an analog, or maybe there is a theory in progress, which is like a characteristic P analog of the classical Kazhdan-Lustig type theory for Lie algebras, but now for this varieties and a characteristic P. Maybe I don't want to. I mean, this is deep stuff, and I don't want to talk about it too much in the general talk.
It's related to representation theory, right? So
yeah, it's directly related. So
field theory is representation theory.
Yeah.
Even to no groups.
Well, there are many algebras that are not universal Welbeck of Lie algebra. So so there's associated to this, it's an algebra which in some sense is good as universal Welbeck of a Lie algebra, whose representation theory in characteristic P you can understand in this exact same detail as you would understand that for a Lie algebra in characteristic P. And the kind of stuff, the kind of Kazhdan-Lustig theory that answers this, there's a certain, Kazhdan-Lustig theory, the very basic thing is the Hecke algebra. And the analog of the Hecke algebra is the monodromy of this equation. Hecke algebra is what? It's a quotient of some braid group by some relation. And here the braid group is a fundamental group of something, and the relation is some. Okay. So my goal is not, rather than to go into this depth, is to explain some really basic, well, you can call, I guess I call it analytic, although, like I said, it belongs really to Whittaker-Watson type of argument. So I don't know, an analyst probably will consider this childish, which is fine. But it's, so this is how you actually get your hands on the monodromy of these equations. And maybe I'll say one word is that, right. So maybe we'll come back to this slide in a second. So, so maybe to have some kind of feeling for what's going to happen is the kind of functions we're going to consider. They're all very fancy generalization of Gauss's hypergeometric function in the differential case and the corresponding Q analog in the difference case. And what's the Q hypergeometric function? So I hope you've seen, well, you know, if you open Whittaker-Watson, it's one of the first things you see, but it's the hypergeometric function is an expression like this. In the Q situation, these Pohammer symbols are defined by, are ratios of, we had the Q gamma functions, and the ratios of successive values of Q gamma functions are defined, are this Q analog of Pohammer symbols. So anyway, this is this generalization of Gauss. I mean, this is called the Q hypergeometric function. And one I want to point out, this solves the variable z we had before, the curve counting variable. Here has the meaning of this is this variable here. This is a power series in z. Remember the equations themselves were written as power series in z, and the solutions we also write as power series in z. So this is the kind of thing it is. Now, but you look at this. That also this expression here involves three other parameters: a1, a2, and 3. And classically, in these other parameters, you also get linear Q difference equation. This classically known as the contiguity relation for hypergeometric function. In other words, you have one object that solves a second order, a 2 by 2 system of Q difference equation. It depends on some parameters. And its function of those parameters, it also solves a Q difference equation. And so the geometric origin of this is, maybe I should, we had this picture about rational curve. We had this picture about rational curve in X, and the extra variables, first of all, the Q, the variable Q, this has the meaning of Q is really just a variable in GL1, if you want, that acts on P1 preserving 2 marked points. And all other variables in the equations are some automorphisms of X. So as you count curves, you can count them equivalent with respect to all automorphisms you have in a problem. And so if you have if your Schur's curve has 2 marked points and it has an automorphism rotation, this is that Q. And if your target has some automorphism, say A, then this also enters the problem. And so this is all the Q that acts on the source, that will be the Q in the shift of Q difference equation, and all other variables, which like the variables A1, A2, and 3 here, they really geometrically means the automorphisms of your target variety. And this particular function, enhances the hypergeometric function that really counts just for the simplest possible. So if you think of symplectic singularities as equivalent symplectic singularities as some kind of zoo or tree of life, then inside there's the basic organism in this. There's the somehow unicellular organism in this zoo, and that is well, I can't have a talk about symplectic resolution without somehow we mentioning the mother of them all, and that is the resolution, which is just the resolution of the usual cone by blow-up. So if you take T star P1, the cotangent bubble P1, this is a blow-up of a cone at the vertex, and this has a million other interpretation like that cone given by this equation. This is the condition of this is the nilpotent cone in the simplest possible Lie algebra of them all, this SL2. So this object has this is really the simplest object in the world, in the sense that only has, if we're going to count curves, well, in this geometry it's really easy because it's just really only one curve in this geometry. There's not so much to count. But and then this is in the sense that this is the simplest symplectic equivalent symplectic resolution there is, and the Gauss's hypergeometric function is the simplest, or Q hypergeometric function is the simplest kind of functions to which the theory I'm going to apply, discuss applies.
But you get only one parameter, not three?
Yeah, it's here you get two parameters. So in that equation you get two parameters. The third parameter, you should really, well, I can tell you what you do. And so now we come, we come to the actual. Now we come to the actual content of the talk. So everything I said so far can be summarized in saying that there are some remarkable Q-difference equations of a certain interest in several branches of mathematics that include the kind of stuff that people from all over the math work, and I'm going to try to tell you something hopefully new you didn't know about the monodromy. And so this message will consist of 2 points, and here's the main point number 1. The main point number 1 is that we have like this hypergeometric equation. So what do we have? We have two sets of parameters. We have my variables, which I denote Z, and some other kind of variables, which I denote A. And in both sets of variables, they satisfy Q-difference equation. In both sets of variables, the equations are regular, but they are not regular jointly. If you ever had a course in D modules, or heard something about it, there's a very deep theorem of Deligne, but just great many deep theorems of Deligne. One of them is that can never happen for differential equations. But so if you have a differential equation, and it has some divisor of singularities, it's enough to check regularity at the generic point of each component of this divisor. But for Q-difference equation, it fails really badly. We'll get to that in a second. And how this manifests itself is that, so this manifests itself by the fact that, first of all, if you have two groups of variables, if each of which goes to 0, then the solution grows polynomially. But if they both go to 0, they grow super polynomially. And in a different way, you cannot write a basis of solution which is holomorphic in a region of this form. And for each one of them, you can, by basic theorems, in each group of variables, you can write a basis of solution. But if you want to do it for both groups of solution, that's not going to work. And so this is, like I said, this is extremely simple. And you can have a look at a one by one example of that. It's really, so look at this system. And if I shift Z by Q, I get A, and if I shift A by Q, I get Z. So this I can solve by a function like this. And you see if Z or A separately go to 0, this grows polynomially. If they both go to 0, that grows super polynomial.
You have an extra word. You should say which is regularly separated, but not
Yeah, right. Pasha is priceless in terms of, and for everything else, there's MasterCard. So this is that clear? In other words, if I look at P1, this is the equation, P1 cross P1. It has divisor of singularity, just the toric divisor of P1 cross P1.
So this is the difference equation?
This is the system of difference equation. Yeah, this is it.
And this phenomena cannot happen in differential.
No. I mean, basically, the reason is that you see, but you have a differential. I mean, maybe the easiest explanation. You have a differential equation. Its singularity means a matrix has to hit a pole. And if you have a difference equation, means the matrix has to have zero or pole. Maybe this is okay. Maybe it's not the full explanation, but this cannot happen. Yeah.
Even more drastically super polynomial. This is super polynomial, but only mildly.
Well, I don't know. You just of course you can. This is enough. This is enough for us. Right. So in other words. So if I look at the singularities of this equation, this is the singularities of this equation is where z or a are 0 and infinity. So this is a union of 4 components. At the generic point of these components, solutions go polynomial as I approach them. But if I approach a corner, I grow super polynomial. Is that clear? And similarly, it's true for if I want a 2 by 2, more interesting example, 2 by 2 example, take the Q hypergeometric equation. The function I wrote is one solution, but then there's another solution. Since it's a 2 by 2 equation, another solution will have this kind of prefactor in it. And for a Q hypergeometric equation, we're going to go back here. So you see here you have a variable in denominator, and this means here I have something. This is holomorphic in Z, but in this kind of variable, this will be only meromorphic, and I cannot find a solution that will be holomorphic in both Z and A. So I'm going to say that this is in fact a feature and not a bug, and it means that this means in a neighborhood of a point. So now we look at a point which is a point like this. It's a point where both A and Z are 0. From this point of view, it's a regular point. In a neighborhood of a point, we have not one kind of solution. We have 2 kinds of solution. Right? So we have what I call the Z solution. So the Z solution is obtained by, so we view this as an equation in Z. We solve it by a power series in Z, and the coefficients of these solutions are meromorphic in A, and their poles will in A they will accumulate to the point I. So this is my equation. In Z is holomorphic, but in A has blue is Z. In Z it's all right, but in A its poles accumulate to 0. And then there's the exactly diametrically opposite A solution, which is just exactly the same. Exchange the roles of 2 variables. And then, that means we have 2 fundamental solutions to the same equation. It means we can do just what Birkhoff did. So if we have 2 solutions to the same equation, take their ratio. This will be some elliptic matrix because they both solve the same Q difference equation. Their ratio will be therefore Q periodic. And for lack of a better word, maybe one could truly call a pole subtraction matrix, because what really happens is that this elliptic function will have some zeros and poles, and we had poles in A, and we trade them for poles in Z because we hit it by some elliptic map function that takes poles of one kind and transforms them poles of the other kind. Right? And so we can now want to compare and contrast. So this is maybe the central slide. So we want to compare and contrast. So this pole subtraction matrix is just like monodromy matrix. So in a sense, it's a ratio of 2 solutions to the same Q difference equation. And so we're going to compare and contrast the two. Well, the first point about it, they're both elliptic, which means it's matrices of elliptic functions. So that's good. But one is really global or analytic in nature. It means it requires analytic continuation. We start with some function, and in principle, we start with a solution. Maybe if we're solving by a series, we get a series, and then we need to analytically continue that series and compare it to some other object. Whereas this pole subtraction matrix, everything happens in a neighborhood of a single point. And so you don't need to go, if you want to really actually do this pole subtraction, you can do it with a computer algebra system, because it really is a question of finding an elliptic, you're really looking for an elliptic function that kills one pole at the expense of introducing another pole. That's certainly completely algorithmic. There's no, this is computational elliptic curves. There's no analytic continuation in it. And now the key point is that pole subtraction, well, what I wrote here, constrains the monodromy. And how does it constrain the monodromy? Because since it's a key point, I'll come to this side to emphasize its importance. So I have solution near z equals 0, and I'd like to compare the solution at z equals infinity. By definition, this comparison is the monodromy. Instead, what I can do is I can use my pole subtraction matrix to convert it to a solution at near a equals 0. What's the solution near a equals 0? Well, the solution near a equals 0 is some series of this form, right? where the zeroth coefficient in this solution, well, that's the original term. That solves the equation, the very degenerate case of my equation, namely when a equals 0. Is that clear? If I have a solution, its initial condition is to find its initial condition, well, I just plug in a equals 0 in the series. And that is going to solve this. I had some interesting equation. And from that interesting equation, I got to a very, very degenerate equation. Namely, I took my parameter and I set it to 0. And so that says that if I want to analytically continue this object, since so this is the solution of some Q difference equation in A. Everything is determined by just F0. So if I can analytically continue F0, I can analytically continue the whole thing. And so therefore, analytic continuation here is just the monodromy of a very, very degenerate equation, which I plugged in a equals 0. So that means the function I want is one side of this commuting square. Now that's is that clear? So in the geometric context, what this means? So in the geometric context, we have this.
That's a small question.
Yeah.
You can't think of the local pole cancellation as also an analytic continuation, but also the blow up. If you were to blow up at the corner, I mean, it might not make your life any easier. So I'm just asking.
Maybe you can. Yeah, I don't know. Yeah, but it's really there's no analytic. Really, if you think about this, there's really no analytic continuation required. You just have, you look at your solution. Maybe I'll go back. Imagine you have a solution like a hypergeometric equation. Has some pole where you didn't want that pole to happen. There's unique term you can add. First of all, that pole subtraction matrix is triangular. We'll get to that. It's triangular matrix. And you can find every term in that matrix by some kind of Gram-Schmidt. By Gram-Schmidt meaning every term in this matrix is determined by which terms it's supposed to kill at the expense of which poles it's allowed to introduce. So in any way, there's an answer for what the whole matrix is, so we'll get there. So in the geometric context, these variables had names. These variables, Z was counting the degrees the degrees of the curves. And so if I set z equals 0, this becomes very easy. It just means I don't consider any curves. There's somehow nothing to do. It becomes an equation with constant coefficient we can just solve. So the z equals 0 example, so I have two systems of two equations. If I plug z equals 0, the other equation becomes extremely simple. I can just solve that. But also, if I plug a equals 0, geometrically means if a was an automorphism of my variety. If I plug that to equal to 0, it just means I take fixed points with respect to this automorphism. And most of the time, it's much simpler variety. But in fact, the way you read it, it's not like this. The way you actually use it backwards. You take, yeah, so this is, I mean, you can use it both ways. You can say that fixed locus is a simpler variety than my x. You can use it like this. But much more powerfully, you can take your variety and embed as a fixed locus in some bigger variety. And then this gives you a stronger constraint. If you think about it, in the end, it's going to give you a stronger constraint than what I said here. But let's not go there. Is that clear? So this means in the geometric context, this kind of games let you completely compute the monodromy of the A equations, because z equals 0 is just a trivial equation, and it really lets you get your hands also on the other equations too, because of that trick. And now main point number 2 is that in fact one can compute what that pole subtraction. I mean, although it's like I said, if you look at actual equation, it's algorithmic to compute what it is. But in fact, you don't have to do it algorithmically. There's a synthetic answer for what this thing is in the geometric context. And what it's some elliptic matrix that has to somehow connect the fixed locus. I explained it. It's some equation. So maybe I'll catch here. So here's the equation for x, and here's the equation for the fixed locus. So there has to be some elliptic matrix that somehow connects the fixed locus and the ambient space. And what in fact really is, it comes from a certain correspondence between the two in the current elliptic homology. And so, of course, this is maybe not the place to, well, it's certainly not the place to start the discussion of how this actually goes. But it's easy to explain the gist of the argument. In the end, so what do we want to do? We want to cancel some poles. Right? There's some poles. We want them to go away. And it's in a million years of human existence, we haven't come up with a more effective argument for pole cancellation than geometric ones. Namely, both poles and their cancellations are best explained, well, certainly in my opinion, are best explained have to do with through localization formula covariant cohomology, covariant K-theory, covariant elliptic cohomology. And an example, so maybe we'll start with an example. So think of Wild character formula. Okay, I suppose most of you have seen Wild character formula. It's some ratio, and it computes a polynomial. So the reason it's a ratio, because you compute it, you think of the irreducible representation as you realize it in sections of a line bundle on a flag variety. And you compute this using localization. So this writes, this gives you the trace as a rational function. But it is a polynomial because it's really the trace of some group element acting over a section of a line bundle on a complete variety. Right? I guess I wrote it down. So you realize your irreducible representation as, well, you can say the Euler characteristic of some ample line bundle on the flag variety. And you compute the trace of your group element by localization formula, which means you look at the fixed points of this group element in the flag variety, which will be indexed by the Wild group. And corresponding to each fixed point, you get a rational function. And this is, you know ahead of time this poles in this rational function will cancel. Right? And so more generally, if you have some scheme of any kind you want, such as moduli of maps from P1 to your target variety, and if you have a coherent sheaf, or if you have a coherent sheaf on Y, and suppose you have this is equivalent with respect to action of a torus, and the torus acts such that if I take the support of my sheaf and I intersect with the fixed locus of the whole torus, I get this intersection is proper. Then the action of so if I have an element in the torus, its trace in the Euler characteristic of that sheaf is well defined as a rational function. And you can tell precisely where the pole of that rational functions are. Namely, the pole happens precisely at those A's, such that if I specialize A, my fixed locus may increase. And if it increases so that the intersection with support is no longer proper, then I hit a pole. Perhaps if you haven't seen this before, I failed to explain this very basic phenomenon. But if you have seen it before, I hope I've reminded you of this extremely basic phenomenon. So anyway, there's a very good geometric understanding of when in expressions like this, where is it, how exactly poles are going to appear, and the kind of and the variety and the geometric, so this elliptic object we want. This is some improved version of. So we want a correspondence between a fixed locus of a torus and the ambient variety. And this correspondence is some improved version of just attracting manifold. So the very basic Lagrangian correspondence between fixed locus and the ambient space is just a set of pairs, such that if I act by a torus element and let that element approach to 0, which is incidentally the same 0, the 0 here. Remember, in my difference equations, I also wanted some torus element to go some end of the torus, and that is the same. So that 0 here means the same as the 0 there. So if you have the correspondence of a set of pairs, such that if I act on X by A and let A go to 0, I get Y. So this looks like this. I have a component of X, and I look at all the trajectories that flow into this, and there will be a Lagrangian correspondence. And there's a lot of work in math and somehow that involves using this, and you can't really like take the closure of this correspondence and expect something nice to happen, even in K-theory, let alone elliptic homology. But there is a way to define some version of this correspondence elliptic homology. And this will be the correspondence we want. And so this is the technical name for this is called stable envelopes. And that's I don't know. So this is so maybe I'll say one word about this. I think my next slide is the last slide, and so this is a certain technical point I want to make sure. Yeah. So if you just take this correspondence, if you just take this Lagrangian, this is not closed or anything. So you can take its closure, but even in K-theory that sounds stupid because you don't just take like structure sheaves and closures in algebraic geometry, and certainly you don't expect in elliptic homology one has to have a smooth variety, smooth manifold to get working. So you don't really expect anything nice to happen with the closure. But there is a way to correct for the singularities of the closure by adding some lower. So you can think there's a way to correct by adding adding some tails to this attracting trajectory. So there's a way to correct for this to have a well-defined object. And this is what this theory of stable envelope achieves. And the theorem I want to say is the following. That we might recall that we're looking for this pole subtraction matrix that starts with the Z solutions, or start maybe, let's start with the A solution. The A solutions are parameterized by, they correspond to something happens on this, the initial conditions for this A solutions are a solution of the quantum difference equation for the fixed locus here. And we'd like to go to Z solution, means we'd like to go from the K theory of K theory of this fixed locus to the K theory of X, but also has to be a function of Q. So in order to go from K theory of fixed locus double bracket Q to K theory of the ambient space double bracket Q, and the theorem we proved is meaning that this map is the Q expansion of this elliptic stable envelope. So this is, and this elliptic stable envelope, the way it's used, the way stable envelopes are used is their basic input in a certain construction in geometric representation theory, and therefore this leads you to describe also the monodromy in the same language of a geometric representation theory, but now in terms of elliptic quantum groups, if you want. So this is now my last slide, at which point I stop.